essentially what you guys are developing in Exodus is a new type of propulsion device that's producing over 1 Earth gravity of force using no propellant, and you've done careful testing in hard vacuum that indicates the force isn't based on known electrostatic effects, right?
That's correct, yeah. It's, we've discovered that it's based, most likely based on the electrostatic pressure force. You know, electrostatic pressure has been around a long time, but I think with careful experimentation you can actually see this force. It's not the easiest to reproduce, but it is. It's pretty clear to us that looks like that's what's going on. And there's 2 components to it. There's a volume component and there's a surface area component. And it kind of falls out of the conservation of energy, so, which is nice. You want to be able to start from first principles, work your way down to something that can help you engineering-wise account for what you're seeing. And the electrostatic force and what we call the divergence in E force, we shorten that to divine. That's the mathematical symbol for divergence. That's what we named it. So, but it didn't start out that way. Like I said in the interview, I was looking for the conversion of field momentum to mechanical momentum, sort of the analog to the Feynman disk Richard Feynman came up with in the 50s. Gave that as a homework assignment to his students, that try to ask them where the momentum came from. Okay. The disk that was charged, a spinning disk. So that angular momentum case was realized experimentally in the 70s, but he was right about that. So since the early 90s or so, I've been trying to look for the linear analog to that. When scientists try to look for the linear analog to that, they discovered this other momentum called the hidden momentum. The hidden momentum is a very strange thing, but it's basically a relativistic effect that counters any linear momentum you have in the system. So this is the reason why bar magnets don't move with an applied electric field, and so on and so forth. So, but because it's a relativistic effect, I thought that perhaps if we were to make the charges static instead of relativistic, you might see that momentum. And when I first met Drew in 2016, my wife and I thought that that's what Drew stumbled across, a better way to do that. The experiments that I did in 2010 and 2011 kind of suggested it. It showed some forces, but Drew's was very profound. So we went down that path. And that was a very simple path to go down, because you're trying to put charge into a volume, create your magnetic field, watch the magnetic field collapse, and then which creates a second E field from the Faraday effect, and then have those Faraday effect move the static charges in the system. Very simple manifestation of conversion of field momentum to linear momentum. So for a few years, a couple of years, we tried to improve upon that. But when we did the math and then we did the experimentation, it turns out the forces that we were seeing could not be accounted for by the current measurements that we took at the time. Okay. So we had to take very high-speed current measurements to see the magnetic fields, measure that, and then determine what the Faraday field would be to see our forces that we were observing. They weren't there. We were way off. So it's like everything in science. Even if you believe something for 20 years, if the experiment does not pan out, you can't believe the theory. That's just how nature is. We don't get to determine what nature does. We have to uncover what nature does.
Well, and so I want to stress this is truly and fundamentally new. You guys have found something that hasn't been explained before. And one of the things, again, I want to address and head off at the pass, criticisms about this. Past claims by other inventors about field effect propulsion have been attributed to experimental forces, or experimental error forces like ion wind, and so that's not the case. You guys have ruled everything out. The other thing that I absolutely want to stress is that you are NASA's subject matter expert on electrostatics, right? I mean, you are experienced PhD physicist working with this. This is your field of specialization. There's probably nobody else in the world who has the level of skill and knowledge and expertise that you do. So this comes right back to your level of expertise, right?
That's true. That's true. And once we learned that the conversion of field momentum to mechanical momentum was not what was causing the forces that we were seeing, then we had to go back to the drawing board. And it took us about 6 months roughly to figure out what was needed to make the force. And learning that currents were not needed, magnetic fields were not needed, now we were dealing with an electrostatics problem. Well, that I know a lot about, because as you say, I am an expert in electrostatics. I don't know if I'm considered the world expert, but I am, for the agency, I am. I do have a lot of friends that are in this field as well, that I've shared this discovery with, and they're equally perplexed as I am. But it does seem to be an electrostatics effect. Basically, all that means we need charge to create the effect. You need fields to create the effect. We don't need currents. We don't need magnetic fields. And we have to, as an electrostatic scientist, we have to be sure that it's not an ion wind or a Coulomb attraction to a wall or a chamber or to a floor. It's a lot simpler to rule out all of the things that it could be when you don't have a current, because now you remove the magnetic field component. Now you're not coupling to the Earth's magnetic field or some other effect. So it does leave, it certainly makes it a lot easier to believe that it's just electrostatics if you can remove all doubt of what it could be. So that's what's exciting about it, is that we know how to prevent false positives. It doesn't mean they don't pop up every now and then, because they can, and they do. There are other effects. So we try to minimize all of them. And as soon as another physicist or someone comes around and says, have you tested this, have you done that, we will immediately do that if we find something that might be giving us a false positive. Nothing drives us more crazy than a false positive. My time is valuable. Drew's time is valuable. I have a full-time job, 3 kids.
Yeah.
And I have a consulting business. I do not want to waste time doing something that is not real, that is not worth it. Drew is the same way. So we have to be 100% sure that what we're seeing is correct and real and reproducible and leads to the next experiment. If A is correct and B is correct, then C has to be correct. So we've been following this progression since 2018 now, building upon it, improving upon it, and trying to increase the force density with every test article that we make. But because we're self-funded, we can only travel in one straight line. We can't attack all of the different possible concepts that can arise. The science is very general. It's not very specific. It tells you in general what you should build, what you should do, but it's not very specific. So it's open to a lot of interpretation.
I want to get into this term asymmetrical electrical pressure, which comes out of older work in this field, right? There was T.T. Brown's research into asymmetrical capacitors, effects that were observed in antique Fizeau condensers, which ended up later being called something called the gravity capacitor. So what makes your device unique?
So where we're different here is, I think the fact that I would say that we would understand it. And that's important. It's not just an experimental test and then where do we go for the next experiment. We actually have physics to say this is why it works. And then if that physics is correct, that should explain the next experiment, and then that should explain the next experiment, and that should explain the next experiment. So 1,500 experiments later, that's where we're at. We're following the same path until we find an experiment that proves it wrong. So in doing so, we've uncovered a lot of nuances from the experiments. And one of the nuances is the fact that there are 2 types of charge, free charge and bound charge. That's known very well from electrostatics. So, but we can take advantage of them because they have different contributions to the force, if you will.
One of the things that makes this device unique is that the propulsive force begins once the device is charged, right? So that makes this device really unique. And there have been, I guess, concerns about this possibility of like violation of conservation of energy, right? Because if you're putting energy in to charge it and then it generates force until it discharges, do you see any potential conflicts there?
Oh, absolutely. I mean, as a scientist, it's very mind-boggling. right? Because we can't explain how, when we turn the power off, it's still there. Now, the physics will tell us that free and bound charge does not need a power supply. Static electricity does not need a power supply. So once you apply the charge to a geometry, as long as the fields exist, the force should exist. But that doesn't rest easy with myself or other physicists of how come the force continues to act. Because now you're doing work without putting additional energy in. It's a problem.
So in terms of thrust, right now, I believe this is generating, again, 1 Earth gravity, but that comes out to being, I believe, millinewtons or micronewtons in terms of overall thrust. What do you think the upper limit is for this? And again, I believe Drew had mentioned he hopes to be able to generate 1 kilogram of thrust in the future. Do you think that it could generate that in the next year or so? And do you think that it can go beyond that?
Right now, we don't have an upper limit, at least in terms of the physics of what the force could be. Since we don't quite understand the microscopic foundations of it, we don't know what the upper limit would be. So the math does not tell us. So if Drew projects a kilogram, maybe we could get a kilogram, not sure. We have to go to very different routes experimentally to prove that. So we'll need new technologies, new materials, new test setups. There's a lot that could be done. We've just basically scratched the surface as to how we can take advantage of this force. There's a lot more to go. This is chapter 2 of a book.
Yeah.
There's chapter 0, chapter 1. We're basically chapter 2 of probably a 10-chapter book, is what I believe. So there's a lot that can be done. There's a lot of different paths stewing in our background that we're trying to encompass, but it'll take time and funding to do that. But there's no theoretical reason why we can't generate more thrust than we are, at least based on the equations.
Well, and speaking of, this long-term path to testing, refinement, and evolving this design. So Drew, again, when I visited yesterday, showed me a stack of thousands. I think he said something like 3,000 tests that he has run in the past. And I think his model has been to test and then change one variable and test again. And again, an enormous stack of binders. He's very good about storing his data. I think that shows the kind of work that you guys are doing on this, right? So you're putting a lot of time and energy into doing this right, refining the model, and basically improving efficiency over time, right?
That's true. I mean, we've made roughly 1,500, 1,600 test articles, but they've been tested multiple times. So that means it could be 3,000 tests. I'm not exactly sure. It's hard to count them.
Yeah.
But he does have the notebooks. He has the data. He has the images, the videos saved. So he is documenting what he's doing since 2020 very, very well. Prior to that, many of the notebooks are here, where we didn't have the high vacuum chamber. This lab was done in air tests, and all the test articles that we tested in that basically a year and a half are on the wall behind you. So the documentation has been outstanding so far, but it will take years to go through that data, to be fair, because it's not something that either one of us really has the time to do. All we can do is look at the test results and then determine qualitatively how well it performed. But it will take some time to go through that data.
So in terms of this model, and in terms of, I guess, extending our knowledge of physics, does this point the way towards even more powerful, I guess, approaches to propulsion in the future? And the reason I ask that is what you've discovered really seems to overturn this idea that propellantless propulsion is impossible, right? And so once that door is open, I'm wondering, how many other ideas might come out of it?
Oh, I think a lot. I think we're creating a force from essentially nothing is very profound. Because you have to ask the question, if you're creating a force from, we believe, the vacuum, can you not create energy from the vacuum? I mean, they're commensurate. So what is nice about it, it can, I think, give you a little bit of insight into the structure of the vacuum. And I think scientists, beyond what I've done, will try to explore that a little bit further. There's a lot of unknowns about the energy of the vacuum.
Yeah.
How much is there? What can you do with it? Can you manipulate it? Can you alter the energy states of the vacuum? Does it have an effect in real life? So I think, I don't think we've done very much work in that area. I think that's a whole other field of physics that people can explore, should they be willing to. But in terms of the forces that we're making right now, like Drew will tell you, we've been focused mostly on DC. There's no reason not to go AC or high frequency AC or other types of alternating current.
Okay.
So like I said, we're just scratching the surface of what we can do, what we can take advantage of. And so to answer your question, yeah, the future is wide open. I don't know what the bounds are. We do know that we can stack these devices to have the forces add up. We do know that we can run them in parallel. We know that we can run them over and over again. We can have on and off switches if we want them to have on and off switches, or we can stack the charge in there and just leave it in there and then keep adding more and more stacks to it. All of those things give you ideas of what you'd like to focus on and what you'd like to increase the thrust in, how you'd want to do that.
Yeah, one of the things that I understand is that you can approach this from kind of a semiconductor manufacturing process also, right? Using vapor deposition for these layered metamaterials, and then by applying the charge, the voltage in a certain way, you can actually, as you mentioned, create stacks of these, create grids, and approach this from kind of a mass production way, right?
Sure. I think that would be a long-term goal. I think that's one thing we'd like to do, because we've learned, unlike Thomas Brown and the others before me, voltage is not the critical dial that makes these devices move. It's electric field. And all that means is that you can have a very strong electric field in a very small volume with a very small voltage. You get the same electric field, even orders of magnitude than T. Thomas Brown did. So you don't need the large structures to create the large forces. So that gives you the idea that, wow, we can stack these things, we can microscopically make them, they can be vapor deposited, they can be thin films, whatever field of research, chemically vapor deposition, physical vapor deposition, however you want to make them, that will be beneficial. So I don't see the upper limit there. It'll be based on breakdown of materials, breakdown strength of materials. How much field can you hold in a very small volume? Those are the kind of limits. More material limits, not physics limits, more materials limits.
Yeah.
And since we're always generating new materials all the time, why not, increase the voltage a little bit, increase the field a lot. So it's exciting to think about what the possibilities are.
Well, and yeah, the reason I asked about that manufacturing process also is I'm familiar with system-on-a-chip manufacturing for computer chips, right? And I'm not necessarily sure if you could fit everything onto a chip, right, especially in terms of high voltage and things like that. But there is this exciting idea of being able to mass produce something and just insert it into satellites for orbital adjustments or something like that.
Sure.
I mean, even something that simple could be transformative.
Oh, absolutely. I completely agree. And should we get funding someday to try that? It'd be a fun thing to try. There's no reason not to try.
Yeah.
So that would be a nice long-term goal. A nice little solid-state device. Turn it on, it gives you thrust, and turn it off.
In terms of physics models, you're using, standard quantum mechanics for this, right? But do you think that this may offer support for things like this polarized vacuum model or anything like that?
Really, our only contribution to the quantum mechanical portion of it is the experimental one. So we know that the forces that we should get classically, we know that we're not seeing.
Okay.
So that means we're off by a factor. But what factor are we off by? Well, it turns out we're off by a factor of alpha squared. That is not at all surprising. Alpha is the coupling between fields and charge. Alpha squared is a quantum mechanical. Alpha, the fine structure constant, is a quantum mechanical constant. Shows up everywhere. So that is not surprising. So all we know about quantum mechanics is that physically, to see the objects move, we have to pay the quantum mechanical price of alpha, that coupling between fields and charge. And it's less for the bound charges than it is for the free charges.
Okay.
That is our definition of alpha. Every field that has or discovers an alpha comes up with a new definition. So alpha is the definition it has many definitions, but it's the ratio of the electrostatic charge energy divided by the energy of a photon of the same wavelength, if you're looking at the pure physics energy. But there are many other definitions of alpha, and they pop up everywhere. So our definition of alpha would be the ratio of the force of the strength from an E field of the free charges divided by the ratio of the strength of the energy of the bound charges. 1/137. That's what we see experimentally. It's pretty cool. Well, but beyond that, the microscopic level of what's happening, because that's the real connection between our force and quantum mechanics. We haven't really done that.
So our free charges would be, could we say that that is electrons then, and then bound charges would be ions inside of the dielectric?
Well, they could also be electrons, right? You can trap electrons into your hair or balloons, or, you know, most charges are probably going to be dominated by electrons, because electrons are easy, they're lightweight, they can move around. They do transfer easy, but ions can too. But whatever's bound is not able to be mobile. So you can easily have electrons that are trapped too, just like ions can be mobile. So it's not a distinction between electrons and ions, but it is a distinction between bound and free. And that's what's interesting. So the bound charges, a lot more energy has been put in there to shove those particles, those charges into a dielectric, you know, to begin with. Much less energy than it would have taken to move electrons around in a metal.
And this will work better, much better, in vacuum chamber testing also, right?
Well, the benefit of going to vacuum is that whenever you're trying to encompass very high electric fields, you're going to hit the breakdown of the gas. Oh. But if you don't have a gas, then the limiting factor is not gas breakdown, it's what we call field emission if you get to high enough vacuum. So that's the benefit. We can get 2 orders of magnitude higher in electric field if we just do it in very high, high vacuum. That's why we do the tests in high vacuum. Otherwise, we're very limited to what voltages we can apply in air. So a test article that works well in vacuum will not work in air, most likely, unless we do an outstanding job of coating it in a dielectric, a very thick dielectric. But that increases the weight significantly if we have to immerse everything in epoxy or pot it or something like that. So that's not really beneficial. So we'd like to optimize the vacuum version that's lightweight, as thin as possible. Let the fields escape, who cares? They're not having any negative effect as long as they're inside the Faraday cage. As long as there's no gases to mess with you, you should be okay. Much easier to do it in high vacuum than air. That's the irony. The air tests are nice. They're good for demos, but there's limitations to what we could do in air. We want to see the forces moving. That means it has to be lightweight. So most of our air thrusters are made of styrofoam because they're very lightweight, but they're also encompassed. So you have to encapsulate the thruster.
Yeah.
You have to prevent that ion wind. The minute you have a current or an ion wind, the force either stops or goes in the other direction because of the ion wind. So we try to encompass them. But in order to see it move, it has to be lightweight. You have to overcome the inertia. So that's why most of those thrusters that you'll see behind are styrofoam thrusters. But in vacuum, that's not the case. We don't need styrofoam. We don't need to always put a dielectric in between. The vacuum is an outstanding dielectric. We've made vacuum dielectric thrusters for years. But now we're trying to move into a pure solid state, more like you're talking about, where you don't have that spacing vacuum requirement. That kind of helps keep things smaller and thinner and lighter, if you can do that. That's kind of where we're headed.
Yeah, well, and again, going back to what I've already looked at in terms of Drew's construction and testing, I mean, it has been so rigorous and so detailed. He walked me through the vacuum chamber testing and all of the things that can go wrong with it, right? I mean, everything from, making sure that it's pumped down to exactly the hardest vacuum possible, and removing any, removing moisture from the walls. That was something that he had to struggle with. Yeah. He's also using a conductive coated carrier for the test apparatus, yes. And that way it doesn't have potential attraction to the walls of the chamber and things like that. So
yeah, that's key. I mean, you have to shield your test article if you're going to use high voltage. So that means we have to put it in a Faraday cage. A Faraday cage that you test to make sure it is encompassing the field, but then we measure the force, but not on the thruster. We measure it on the Faraday cage. So the whole system as a whole is what we're measuring the force on. So when we do the math, we say, oh, we're above unity. We're not really above unity. The thruster itself by its weight, is above Earth's unity, if we could just isolate it. But we never have that opportunity. We have to connect it with housing, it has to connect it with wires, it has to be connected to a power supply, it has to be inside the Faraday cage. So all of that other stuff, just to make our measurement, has to come along with it. So we're a long way before, you know, having that device be a free floater in the air. You see the distinction there? But we do have to quantify something. So some way of quantifying our performance. And the way we do that is we take the mass of the actual thruster that's giving us the thrust. You know, we take the force that we divide it by the mass of that thruster. So the force divided by that mass is our metric that we use to quantify how well we're doing. How to, you know, quantify this thruster versus that one.
So in terms of progress since our last interview, because I think you and I did an interview on this just about 6 months ago, and I know there has been massive and dramatic change, both in terms of your research as well as the exposure that Exodus is getting. And that's really exciting to see real work that's done with a level of quality and professionalism get noticed and get taken seriously. How have things changed? How are things progressing for you?
Well, for me, it's been nice to finally get it out there. You know, I think as a scientist, that's what you want to do. That's your whole goal. You want to make sure that, hey, look, discover something fun. Now I get to share it with the world. You know, for 8 years, I couldn't tell anyone about this. And that's frustrating because you really want the scientific community to buy in on it. And the only way they're going to buy in on it is if they know about it. But it takes more than that. They have to go back to their lab and do it. And that's going to take time. I've run into a couple of scientists that say they've seen this. But it's going to take more and more over time to believe it. I can't expect anyone to believe it right away. It's too profound.
Yeah.
And that's okay, and that's what I expected. But at least they're interested in it, and that's what's exciting. And maybe they'll come up with something better. Maybe they'll have a better test rig, or maybe they'll have a better material, or maybe they'll teach their students, and their students will teach their students. The same thing as the ion wind thrusters. You know, 20 years ago, no one believed those things worked at all, the lifters.
Yeah.
Remember that? They didn't believe them at all. You know, the French group was making them, and no one believed it. Until other scientists started building them in their house or their lab or at school, at the university, and let the students play with it. And then you know, before you know, there's thousands of people making these lifters, and MIT's making them, and there's a lot of groups out there making these ion wind thrusters. And that's what it needs. What's nice about this is I believe this thruster can go down that same path. It's not like making a discovery in a superconductor super collider or large hadron collider or something like that, where no one could do this experiment at home. Here, this is an experiment that you could do in your garage. In fact, I'm in my garage right now. You could do this, you know, just about anywhere. Now, the high vacuum stuff, that's fancy, that can come later, but you can at least do testing at home. And I'm going to make videos on how to make some of these styrofoam thrusters so you can check it at home and see it with your own eyes, build it with your own 2 hands.
Yeah, I think that's wonderful to get people involved and engaged, right? And yeah. I mean, not only is that part of activism, but I think that it's also part of just education, right? Helping younger people understand how electric fields work, especially electrostatics, which I think is kind of a niche topic, and it has so many applications in everyday life, but it isn't always as understood as it could be.
Yeah, I mean, my field of electrostatics, there's not many folks in this country that are doing electrostatics actively. You can't get a degree in electrostatics in the US like you can in other countries. So it's fun for me. I love to teach the young guys in the lab electrostatics. They love learning it. It's going to take decades. It just does, because it's such a large field of study. It's in chemical applications, pharmaceutical applications, safety and reliability applications. At NASA, we do a lot of electrodynamic dust shields, where we lift dust from surfaces using electrostatics.
Yeah, actually, if I could jump in, that was one of the things that I just learned about your work is, so in terms of, I believe, Mars and the Moon, right? One of the issues is that you get dust coating a lot of, well, just everything, but especially stuff like solar panels and things like that. So you're actually developing technology to use electrostatics to remove that dust.
That's correct. So NASA, the Kennedy Space Center, has worked on what we call the electrodynamic dust shield for 25 years now, roughly 25 years, somewhere in that range. And it was a technology that was given to us from a colleague of ours, Dr. Sid Clements and Malay Mazumdar, who received that technology from the original inventor, the famous electrostatic scientist Shinichi Masuda, in the 1970s. He had 3 students that went to Florida State, where I went to school, with my colleague, Dr. Sid Clements, who also went there. He learned about the electrodynamic dust shield. Basically, it had many names over the years. The electric curtain is what he called it. But so we looked at it and said, well, this could be used for space applications, solar panels, and there are 2 companies now that actually sell these self-cleaning solar panel covers. So NASA obviously has a huge need for this because we can't clean our own solar panels, we can't clean our own thermal radiators, we can't clean our own camera lenses or visors or gloves or boots, whatever. So we've made all kinds of EDSs for so many applications: gaskets, seals, hatches, doors, all kinds of applications. And we hope to implement them on the moon. We have 2 payloads that one has gone to the moon that had an EDS on it, which unfortunately did not deploy on the Intuitive Machines lander a few months ago, back in February. And then we have our payload that's in our lab called the EDS that has 9 EDSs on it.
Okay.
So we have a glass one, a thermal radiator one, a camera EDS, and then we have 6 redusters. And that's kind of cool because that'll take dust from the surface, throw it onto the EDS using our EDS technology to show that we can get dust off of it. So that is a very exciting payload you can read about. That's going to be one of the 9 payloads on the Astrobotics Blue Ghost lander.
I'm wondering if the trend towards microelectronics has reduced some of the use of this area, I guess. And I may not be expressing that correctly, but one of the things I'd wondered was, because it deals with high voltages and it deals with things that are really not suitable for work with microelectronics, are we seeing less work in electrostatics as a result of that?
Actually, the opposite.
Oh, okay.
So that's the electronics industry is what kept this field alive. That is a $6 billion industry in electrostatics that the microelectronics industry has funded. And the reason is they have to remove, like you said, electrostatic fields.
Yeah.
So they use electrostatic equipment to do that. So you're using air ionizers that you'll have in those microfabrication laboratories. You'll have field meters to check for electric fields because 5 volts is not allowed. Your average clothing will have 25,000 volts on it. So you have to wear ESD garments, you have to wear ESD gloves, and ESD floor, ESD mat. That is all from that industry. So they have promoted electrostatics to preventing and keeping down electric fields. So that is one subset of the electrostatics community. It's problem solving, it's instrumentation, it's developing technologies, but it's also safety and reliability of processes. And that is one of the bigger drivers of the field. So you'll go to large conferences that'll talk about electrostatics of semiconductor devices and manufacturing. Huge conference every year. Try to prevent electrostatics from destroying microchip manufacturers. It's very well known. So that would be part of the EOS ESD symposium, the electrostatic discharge and the electrical overstress conference. It's about 2,500 people that go each year.
Do you think you'll be able to present this work on propulsion at those conferences as well?
I don't think so. I mean, their focus is mostly on, IC integrated chips, latchkey prevents, that kind of thing. This conference is very focused on that. The Electrostatic Society of America is a little bit more open. That's more general industry terms: chemical processing, safety, reliability, space applications. That's more general. Pharmaceutical industries, aerosols. A lot of people don't realize your inhaler is an electrostatics device. A lot of people don't realize that your air filters in your homes are electrets, an electrostatics device. So that's far more general, and that's probably a more appropriate place for this, because that's the field that's probably going to advance this technology, is the electrostatics community, because they understand how to work with high fields, how to measure them, how to not hurt themselves with them, and all the implications of having a high electric field, what it does to the insulator, what it does to dielectrics, what it does to the gas, all the plasma discharges that it creates, corona discharges, brush discharges. It is that community that understands that aspect of it.
And I should differentiate also, just for the audience, that so you are currently with NASA. Your work with Exodus is not part of NASA. This is an after-hours project, and many scientists have those of different types. They have their core work that they do for whatever agency they're with, and then they have work that they do after hours. So.
That's correct. That's one of the nice things about working for the federal government. There's not too many perks, but that's a good one. You're allowed to actually work on, allowed to have outside activities. You let them know that. The 10 years I was gone from NASA, that's when Exodus was formed. So I was gone from 2009 to 2019.
Okay.
Before that, I was a contractor for NASA for 10 years. And then after that, I was consulting. And then I was asked to come back and run the laboratory in 2019. So, no, the Exodus is separate. And the only reason I agreed to go back to NASA was because they allowed me to continue that work and keep it separate. So that's what I've been doing.
Oh, okay.
Yeah.
Yeah. So that's an area where there isn't potential points of contention or anything like that.
I can't write grants from NASA to Exodus. Obviously it's conflict of interest, and to keep out of trouble, I just keep Exodus separate from NASA.
Well, and again, I've worked with so many professionals who work in different roles in the federal government. It's not just outside companies, but like a large part of that is participation in outside conferences, as well as doing peer review and like journal publication work, journal editing work. So, PhD physicists at your level are involved in many different projects outside of work. So that's not unusual at all.
Yeah, that's true.
Well, are you planning any more peer review publications in the next few months on this technology?
Well, I do need to release a few, yes. I do need to release the paper. It's gone through the patent process a couple times, but we do need to send it out to the scientific community to review it, for sure. It's not an easy task, considering, like you said, 3,000 tests or whatever Drew's number is to go through. Usually when you have a data set, you don't usually have 3,000 data sets to look at. So that's going to be challenging. I need to find time to do that. But that is certainly something worth doing, and could take some time. I've been dreading looking through all that data because I know it's a lot.
Yeah.
I know it's a lot. So I need to carve out a month or two just to look at it and then see what I can gather from it. But it is difficult. We don't have data analysts on our team. We don't have anyone else that can look at the data all day long. We just don't have people that we can just hire to do that. So it'll have to be something I'll do in my spare time.
Well, and I want to stress that this is a labor of love for both yourself, Andrew, and some of the other folks who are helping contribute to this effort, right? I mean,
yes.
This is something that you guys do because you believe in it, and you have found something, and you're rigorously pursuing it.
That's right. And the team that's been together for many years have all full-time jobs, and we meet once a week just to bring things together, and but it is a labor of love because everyone's done a lot of work on this.
Yeah.
Not just Drew, but all of us have done a lot of work, side work we're not getting paid for many years, and that's kind of rare, I think. It's one thing to work with someone for a year, 6 months, or something for free, but try doing that for a decade. It's a lot.
It is, but I think hopefully one of the things that helps to inspire you is, again, this realization of finding something truly new and novel. And that's one of the things that you have expressed to me several times in the past is, it's coming into it, you had a little bit of trepidation, right? And as you started to look at it more and more and rule out various conventional explanations for it, it was just like, no, we seem to have found something completely new.
That's right. And that's why we have to do all of the validations. And that's why the next validation for me is to get it in space. If it moves in space, then you've eliminated every possibility that you can think of that we can apply, that we can measure in the laboratory, because the laboratory probably has limitations. So we have to get it in space because it is so profound. If it goes into space and it doesn't work, then I will just admit, well, we were wrong. We did everything we could. There was some factor we didn't account for. Don't know what that would be. Colleagues don't know what that would be. But put it in space, if it does move, then we know it wasn't real.
Yeah.
So we have to be prepared for that as scientists, and that's okay. But I'm not going to lose any sleep over that, because I've done everything, 1,500 test articles in, to try to prove that on the ground, that it's it actually is a real phenomenon. Because we don't want to waste anyone's time if it's not. But putting it in space and it moves, well, that's when the world changes. That's when everything changes, because you can't argue that. That's different. Okay, that's not anyone's opinion anymore, or anyone's scientific belief. That is an actual fact, if that device does move in space.
Well, and it becomes usable then, too. You can use it for attitude control, and in terms of systems similar to this in some ways in space, I understand that there are superconducting magnets that are being experimented with only for attitude control, not for propulsion. But still, it's electromagnetic with no moving parts. And again, in their case, they're just changing the position of the satellite, right? So it's very straightforward by pushing against the Earth's magnetic field. But
sure,
there's already a precedent for this in some ways.
That's true. There is an Electrostatic Propulsion Society, right? Group.
Oh, yeah.
Unfortunately, it's not electrostatic. But in all fairness, these are either gases that are ionized, or plasmas that are ejected out, microthrusters. They're in the electrostatics community, because you're using ions and electrons for the propulsion. So you still need a gas or liquid to do this. So this would be a significant increase in efficiency, because the specific impulse is infinity. So it's not easy to put in the rocket equation. But there is precedent for this. So these microthrusters can be turned on. They can be turned on for a long period of time, and they're going to make satellites go to very, very, very high speeds. So when we prove this in space, which we hope we will, we will show that this can be used in replacement of all those thrusters. We won't require gases. We don't have any moving parts or any current that we need to deal with. Electrodes that kind of oxidize over time or anything like that. So it's with any system that's not moving, doesn't have any moving parts or even any moving charge. Well, this will be a good competitor to that market. The forces we believe can be stacked. That's what we've measured. And then we believe that we're over certain gravities. I'm sure Drew might have talked about being higher than lunar gravity, for sure. So on Earth, we don't have enough forces to lift our power supply and our framework and all of that, but we do in space and we do on the moon. So think about that. That's kind of exciting. We'd love to send a CubeSat to the moon and just have it hover around the lunar surface, something just to show a proof of concept.
Well, and one of the things that was exciting to me was this idea of if it generates a propulsive force until the charge is discharged, right, you can run this for prolonged periods of time. And so even though the net force may be small, for things like exploring the outer solar system or potentially even probes to Alpha Centauri or other star systems, you might be able to attain much better travel times than you could with any kind of chemical booster.
Oh, absolutely. I mean, the numbers are kind of hard to believe when you figure them out based on the accelerations that we have. They're very small accelerations, but it could stay on the entire time.
It's additive, right?
It is additive. So get to the moon in 2 hours, get to Mars in 5 days, get to Jupiter in a couple of weeks. It's really insane how efficient this thrust would be in space and how useful it would be. In our lifetime, Tim, you and I, we might be able to colonize the inner solar system with this technology.
Well, it's incremental. I had recently read about NASA's probe. Again, very conventional propulsion system, but what intrigued me was this is one of the latest solar probes, and it's actually scraping the atmosphere. It is that close, taking photos, and we're around 50 years old looking at that saying, we have a probe that's so close to the sun, it's actually touching it. Yeah. For me, that's profound, right? But it's that incremental advance. It is making things better day after day after day, and after a while, it becomes profoundly better, and it seems like that's exactly what you're doing with electrostatic propulsion.
That's right. I mean, this is a game changer, really, because now you don't have to carry thrust with you, or any propellant with you at all. Thrusters can be made small and lightweight, and they can stay on with very little power. You know, it is a game changer. For the space industry, it's absolutely a game changer today, without any significant further advancements. But the real goal would be to change transportation forms on Earth. That would be very profound. Cars and planes, trains, they would look vastly different. And I think the Earth needs that. And I think this could provide it, should we get the forces much stronger, which I don't think that's impossible. So that's our goal. You know, space is our next step, but it's not the end goal. Really, the end goal is Earth. So you can imagine how profound that would be if we didn't need gasoline cars or hydrogen cars or electric cars or trains or airplanes. Now, fuel, how cool would that be?
Well, in terms of incremental on Earth, it seems like maybe something like boats and water transportation might be a place to start, right? Because you might be able to have some of that similar effect where it's a small propulsive force that builds over time.
It's possible. I mean, there's some friction with the boats in the water, but I think people might be more comfortable in a boat than an airplane.
At least starting out.
At least starting out. So, sure. Yeah.
Yeah, that's absolutely amazing. Well, Charlie, let me thank you so much for your time today. It's truly a pleasure and an honor to be able to go over the Exodus Propulsion Technology with you. This is so amazing. And I think, you know, over time, we are all going to see much more of your work in the news. And so, thank you, sir.
No problem, Tim. Anytime. Thank you.